stage is yours. Thank you for that introduction. I'm Ryosuke Sada from Kyoto University. I'd like to begin my presentation on the topic that was just announced. This is the outline of my presentation. First, let me discuss the research background. Research background is progressive deterioration of road infrastructure. The aging of infrastructure has become a major social issue in many countries. For example, in Japan, about 80% of all expressways were opened before the year 2000. So road infrastructure diagnosis is becoming important. The conventional diagnosis method is the hammering test. It detects cracks by analyzing acoustic waves from striking the concrete. However, a lack of experts and the economic impact of road projects are key challenges. So, a simple, low-cost, and accurate sensor-based diagnosis for reinforced concrete is needed. This is our research concept. Our research concept is diagnosis by embedded sensors placed inside concrete. Wireless sensors are mixed into the concrete during construction, and sensor data is collected by inspection vehicle during driving on the road. To realize our research concept, there are 4 key technologies. First one is wireless power transfer from the inspection vehicle to embedded sensors. Second one is wireless communication from sensor to vehicle. And third one is reinforced concrete crack detection by the embedded sensor. And fourth one is sensor localization in reinforced concrete. Proposed system enables concrete diagnosis without expert knowledge simply by driving on the road. Among these key technologies, sensor localization in reinforced concrete is an unexplored area. So in this research, we focus on it. Next is a related work. Now, I'll introduce some representative localization methods. First one is GPS. It provides low-cost position information, but the error is on a meta scale. So it is unsuitable for sensors in reinforced concrete, requiring centimeter scale accuracy. Second one is Wi-Fi-based positioning. It's often used for localization of smartphone, and its accuracy depends on the density of access points. So it is unsuitable for outdoor environments like highways via targeting. On the other hand, DC magnetic field-based localization enables high accuracy localization with a fixed anchor coil. It's not applicable for our concept where the anchor coil moves. If the method supports vehicle-mounted moving anchor coil, this can be promising. So our objective is to realize a localization method that works with a vehicle-mounted anchor coil. Next is a proposed method. In our proposed method, there are 2 main parts. First part is an inspection vehicle takes measurements at multiple locations to generate a series of position estimates. There are multiple estimates. Estimates with a closer sensor to anchor distance are more reliable. So we introduce confidence weighting estimates by distance. Second part is the confidence of each estimate is used to find the final position via maximum likelihood estimation. By conducting confidence weighting, we improve accuracy when the anchor coil moves. Maximum likelihood estimation part consists of 3 processes. So I'll talk about these processes. Process 1 is setting initial values. First step is we set an initial coordinate to the average of all estimates. Second step is we derive the x-coordinate confidence sigma kx based on the distance rk between sensor and the anchor coil ck. Third step is similarly to the x-coordinate, we derive the confidence for the y and z coordinates sigma ky and sigma kz. And fourth step is we repeat step 1, 2, 3 for all anchor coils. Process 2 is likelihood calculation. First step is we calculate x-axis likelihood. We derive the likelihood LKX from the normal distribution using the provisional coordinates mu x and confidence sigma kx. And second step is we repeat step 1 for other axes and multiply the results to find the total likelihood LK of the anchor coil CK. Third one is we perform these calculations for every estimation results. Process 3 is sensor coordinate update. First step is we calculate the sum of likelihoods L1 to Ln and define it as a cost function. Second step is we update the sensor's provisional coordinate to maximize the cost function. Third step is we repeat process 2 and 3 until the coordinates converge. Next is the experimental setup. We use the standard deviation of the estimation result as a confidence. Standard deviation changes based on the distance from the sensor to the anchor coil. So we pre-characterize the standard deviation with 1000 conventional estimates. This figure shows the standard deviation versus anchor coil to sensor distance. For worst case curve fitting, we use the point of maximal standard deviation from each 50 mm interval. Based on the experimental results, we define confidence as a function of distance. This is the experiment of proposed method. Sensor was placed at 0, 400 mm and up to 0, 1000 mm. The inspection vehicle performs 11 position estimates. This set of 11 estimates is a single dataset. And to validate the method, 1000 datasets were prepared. The subjects of comparison are proposed method and the single average of the 11 estimates and the estimation result from the process vehicle. Next is the evaluation. This figure shows the mean error of estimation. Error increases as the sensor gets farther away. The proposed method achieved 23% to 43% reduction in estimation error across all 7 cases. So the proposed method is more accurate than conventional approaches. This figure shows the error distribution of estimates. Error bars indicate the standard deviation of estimation result. the, the error bar of proposed method in this figure, the red bar is smaller than other methods. So the proposed method is more precise than conventional methods. Now, I'll give the conclusion. In conclusion, we propose a platform that can diagnose reinforced concrete just by driving an inspection vehicle on the road. We propose a distance-based weighting method to allow positioning with a vehicle-mounted anchor coil. Our proposed method achieves higher accuracy and precision than conventional methods. In our future work, we conduct a more thorough validation and the structure of actual reinforced concrete. And we have to consider the electronic noise from the inspection vehicle. That concludes my presentation. Thank you for listening.